Hello, this is Mrs. Schroeder. We're going to continue talking about Section 3 in Chapter 10 with Hess's Law, but this time we're going to use our standard enthalpies of formation to calculate delta H. So the enthalpy change in forming 1 mole of a substance from the element in its standard state is called the standard enthalpy of formation of the substance. We give it a special designation with this little F and the little kind of 0 sign, degree sign is called a naught sign. So the value of this for elements is always 0. If I need to find the enthalpy of a reaction, I'm actually going to take the products minus the reactants for this. It's an application of Hess's law, and it can be applied from what we learned before about all the reactions and adding things up and taking things away that we just did with the full reactions. But now we're going to boil it down to an easier form of using Hess's law, which means that if I know what the elements are for something, I can then use that to find the enthalpy of the reaction by using this formula. Okay, if a coefficient is in front of the substances, I do have to multiply it by that coefficient. So make sure you notice that. If it's got a 2 in front of it, I multiply it by 2. Here's a table. I will give you a table. It's on page 833 to 834, and your book is a longer one. This is the one that's a shorter one, which is actually in your textbook in this section. And it gives you an idea of what some different enthalpies of formation is. The delta H is measured in kilojoules per mole, again. So what this means, aluminum is a negative 1,676, which means it's exothermic. It's highly exothermic to react aluminum with oxygen. Methane has still a negative sign, but when I take carbon and I take hydrogen, C plus H2 goes to CH4. In that reaction, 74.9 kilojoules per mole are given off. So not as much. It's less exothermic than aluminum oxide. Again, elements are 0 because the definition, I don't make hydrogen from itself, not from anything else. A couple of them are positive. This would be an endothermic. It actually would take energy to create nitrogen oxide, or nitrogen monoxide, from the elements nitrogen plus O2. That would be an endothermic process. That's what that kind of thing means. So here's an example here. If I have this reaction, hydrogen plus carbon dioxide goes to water and carbon monoxide. And I'm asked to see whether the reaction is exothermic or endothermic. I'm going to go through and find these. Okay, actually I'm going to look at all these. We're going to look up on the table. And if you get to a problem which is not listed in the appendix in your book, you can always Google it if you need to. You just type in standard enthalpy of formation and you get a PDF with a list of thousands of them. Take my reaction, or take my equation. Heat of reaction is products minus reactants. Now, again, 2 moles is because of this 2 right here. Okay? Or sorry, because of the 2 for water. So 2 moles times the 241 for water. Be careful with water, double check the state. Water does have different enthalpies for different states, so check its state. That's the only tricky one. Plus, the other product is carbon monoxide, which is right here. So this is for the carbon monoxide. This one is from the water. And then I subtract off this is from the H2, and notice I'm subtracting again, subtracting the reactants. I see we'll try to subtract one and add another one. Keep your signs right here, be careful of your signs. This one is from the CO2, and add those together, you get 842 kilojoules. Because it's positive, endothermic because positive. Delta H. Okay, so we can do this. We know it's positive, but it doesn't take lots of energy. We get an idea of how much energy it is, how stable it is, by knowing something about that. So for the next one, determine the delta H. This is going to be a practice we're going to look up. So I have this reaction. I want to know what delta H is. Also, I might want to know if it's endothermic or exothermic. So I'm going to look these numbers up. Heat of formation of CaO. When I look that up, it's negative 1206.9 kilojoules. This one, delta H, is negative 634.9 kilojoules. And the CO2 is negative 393.5. So I've looked those up, and I want to find delta H of the reaction. Is delta H of the products, so CaO, plus delta H of CO2. And I check, and there are no coefficients, so it's like 1 times each one. Minus the reactants. I only have one reactant. CaCO3 is my reactant. So these are my products. And this is my reactant. Plug the numbers in. So CaO is negative 634.9 plus the CO2 right here, which is negative 393.5, minus the CaO, which is negative 1206.9. And when I add those up, I get 178.5 kilojoules per mole. So delta H for this reaction is 178.5 kilojoules. It's endothermic, and it takes more energy than the last one we just looked at because the delta H is higher. It requires more energy than the previous one we just looked at, which only had 82 that it required. Another example, this one has a coefficient here, so pay attention to what we're going to do. Delta H for this reaction would be delta H of the product, Fe2O3, minus delta H of the reactants. So I have 2 FeO minus my O2, delta H of the O2. Again, I'm going to look these up on my tables. So once I've looked these up, I'm going to plug the numbers in. Fe2O is negative 824.8. I'm going to subtract 2 times the negative 272.0. I'm also going to subtract oxygen. If you don't find an element listed, it's 0. Remember, elements are always 0. So sometimes you may not see an element listed on your table, but just remember they're always 0. Okay? Put those in your calculator. Make sure you have a negative and negative. So I'm subtracting this negative off, which really means I'm adding a positive. You can use your calculator, or you can do that part in your head. And I get negative 280 kilojoules per mole, which means this reaction is exothermic. So I'm going to use my heats of formation that I've looked up. What you have to remember is that it's products minus reactants. I do see some people that try to switch those around, do reactants minus products. So make sure it's always products minus reactants, like T final minus T initial. And please don't lose your negative signs. Be very, very careful with your negatives. Also, on these problems, pay attention to your coefficients. Multiply by your coefficients if you need to. Much easier way of using Hess's law, and it's set up by the equations that we did the previous day. We can use those to prove this if we needed to. but these are how we would go about using it in a more helpful and easier, faster way to do it. So again, this is Hess's law using heats of formation. We'll do a few more practices in class tomorrow and show you how to do those on your own.